Hello everyone, welcome to this talk of advanced attacks in dAPP, decentralized app, and Solidity. So before to jump to this talk, first I would thank the Arab Security Committee for this opportunity and for giving or sharing with the community of cybersecurity and most of the person that are passionate by cybersecurity. So about this topic or about this workshop about advanced attack in dAPP and Solidity, before to jump, a little introduction about me or who am I. So I'm mssassi Souhail. I'm a co-founder of Crisis. I'm also passionate about cybersecurity, so I make a community in cybersecurity here in Morocco. So we are organizing some CTFs. I'm also an OWASP member in Chapter Morocco. I'm cybersecurity consultant, blockchain developer, and I'm also an instructor at Vert Learning. So if you have any question, feel free to send me an email or send me a message to my LinkedIn account. So the agenda of this talk, we are going to talk about 5 axes. So first of all, blockchain is very large. So we are going to just to focus in the Ethereum network and especially in smart contract deployed in the Ethereum network. So first we are going to talk about what is Ethereum, what is the components of Ethereum. Then we are talking about weaknesses in smart contracts and therefore talking about vulnerabilities in Solidity and how to fix or how to write some secure smart contracts. And finally, we are going to talk about some tool or some about automatization for auditing and analysis of smart contracts. So if you have any question, feel free to just ask them and I will go back to them to the end of this talk. So first of all, as we all say, to understand or to know vulnerabilities in some systems, we should understand very well the system. So now we are talking about Ethereum. So what is Ethereum, or what is blockchain in general? So blockchain, it's a distributed ledger of transactions. So when I talk about transaction, it doesn't mean financial transaction, but it can be just calling a function to a smart contract. It's a transaction. So basically, blockchain can ensure integrity and transparency. So why blockchain can ensure integrity? Because each data or each transaction are stored in the ledger, and no one can touch the ledger and modify it. So it's very hard to alter in the ledger of blockchain. Second thing, it's transparency. So what is transparency? Transparency, if we are in a scenario of a public blockchain, everyone can see all the transactions. So here we can build a confidence between the application and between the clients or between the users. So of course, the first application of blockchain, and as you know it, it's a Bitcoin. So Bitcoin is a cryptocurrency that implement or they add or Satoshi comes with the idea of the proof of work to validate some blocks. Then the idea of blockchain here comes up. But Bitcoin is used just as a cryptocurrency, so it's just used for a financial transaction. Then Vitalik, it's a Russian guy, he came and say, okay, the idea of Bitcoin is great, but can we do it in a general manner or in a general way? So Vitalik here comes to generalize the Bitcoin concept, and he make Ethereum. So Ethereum extend the Bitcoin concept into not just financial transaction, but any kind of transaction. So he makes the logic of decentralized application. So now we have two things. We have Ethereum, which is the network between we deploy our smart contracts, and we have our smart contracts. It's our code. So what is, first of all, what is a smart contract? So a smart contract, it's a piece of code. It's like a paper where everything is written, and this piece of code we can't change it. Why we can't change it? Because in the blockchain, if the code is deployed in the Ethereum network, we can't modify it. So even the person who code the smart contract can't modify this code. So basically, smart contract, it's a code that that behave as a normal code, and we can interact with this smart contract as we can interact as normal application, and this code can ensure confidentiality, can ensure transparency, and can ensure integrity. So okay, so we understand now what is Ethereum. We said it's the network that is deployed the smart contracts. What is the smart contract? But can we write the smart contracts, for example, with PHP or JavaScript, or there is some condition. For the Ethereum case, we have two languages. We have Viper, and it's a language inspired from Python, and we have the Solidity language, and it's the most famous language to write smart contracts in Ethereum network. So here in this talk, I'm going to talk about Ethereum or smart contracts written in Solidity language. So first of all, we are going to look deeper in the Ethereum network and to look deeper in Ethereum components. So the Ethereum components, it's like the OZ model in the network. So there is layers. So there is the Ethereum protocol layer, there is Ethereum network layer, there is the application layer, and there is some tool or interface to communicate with our blockchain. So in the Ethereum protocol, what can we find? So we have some logic behind it, some protocols behind it, like the protocol, for example, of mining. It's like a proof of work, proof of stake, but in Ethereum case, we are just talking about proof of work. So for the person that don't understand proof of work, so proof of work, it's a mechanism that can ensure that miners validate only legit transactions. So basically, to validate a block, you should solve a mathematical problem, and this mathematical problem behaves. It's finding a hash. So, and the difficulty to find this hash can it depends. So the first one to find this hash has the ability to validate a transaction. So the proof of work now it's the fundamental of the Ethereum. But now in the new Ethereum, they think that they transit from the proof of work to proof of stake or to another mechanism, because proof of work it's very they consume very and a lot of resources. So okay, so for the Ethereum protocol, as we say, we have some mining protocol, we have the EVM machine. So what is the EVM machine? So it's very important, this concept. To understand the vulnerabilities of Solidity, we should understand the environment first. So the EVM machine, it's like the case of when we code in Java. So why Java? It's a multi-platform language. So basically, Java, we have the JVM, the Java Virtual Machine, and this in this JVM, we take the code or the language of Java, and then we compile it to some bytecode, and from the bytecode we are calling the right API for any exploitation system. So the same case here in Ethereum. In Ethereum, instead of JVM, we have the EVM, the Ethereum Virtual Machine. So it's a machine that can understand Solidity and can understand Viper, and then they compile it to the bytecode, and then they executed the function call. So okay, so here it's the Ethereum protocol. So it's a very mathematical thing, but you can go deeper and look deeper to understand some very fundamental things in blockchain in general and in Ethereum especially. Then we find the Ethereum networking. So here we are in the network layer. So in the Ethereum network, of course, we have a network, and each network has some nodes, and these nodes are communicating. So of course, this node has to discover his neighbor. So there is some protocol to node discovery. There is some, of course, if we have a communication, we should ensure the confidentiality of information. So we have, for example, an encrypted handshake. We have an encrypted communication. So everything here is handled in the network layer. And finally, we have the application layer. And this is what we interact with, and of course we find here some our smart contract code written in Solidity or in Viper, and of course we have some backend and frontend to interact with this blockchain. And of course we have some tools and interface just to facilitate the communication between the smart contract and between the user. So that's it for the Ethereum components. So now, why we should care about security of smart contracts. So we have, for example, security of web application, we have security of mobile application, security of infrastructure, security of SCADA system. So why there is a need for the security of smart contracts, and what is the difference between security in smart contracts and security in, for example, web application? So here, for our case, Ethereum and other blockchain system are very recent. For the case, for example, of Ethereum, it just shown in 2015. So just five years ago, there is no Ethereum. So, but for example, for PHP, for JavaScript, for C, it's a very mature language, and we already discovered a lot of vulnerabilities, and we know already how to fix them. So the first thing is that Ethereum is very recent, and we don't know how to deal with it. The second thing, the Solidity language requires another philosophy into development. So basically, coding in Solidity differ to normal coding. Why is that? So the problem here in the blockchain, it's that the blockchain is transparent. So everything in the blockchain, and when I say the blockchain, I talk about public blockchain. So everything in public blockchain, it's public. So everyone can see transaction, can see the function, the call function of your smart contract. He can see, for example, if you store some client data in your smart contract, anyone in the network can see this data. So now the developer is in dilemma to know what's the things that he should put in the blockchain, and which the things that he should not put it in the blockchain. So the second thing is that it's just the philosophy to code in Solidity differs a lot of normal coding. Okay, the third thing, and it's the most important things here in the case of smart contracts, is that the smart contract, the case to use the smart contract, or the cases are the most that we've seen are financial cases, or some, for example, a banking application. So it focused a lot on the money side, and of course everything that can that have some money, we drive attention to hackers. So of course, if for example I say to you that there is a mobile application that just handles some normal thing, for example a hospital application or a smart contract that contains a lot of money, of course hackers will look for vulnerabilities in this smart contract. So as hackers call it, Ethereum or smart contracts are the Disneyland for hackers. So that is for why we should care about security in smart contracts. Now, what is the problem to security in smart contracts? So it mentioned, and as I mentioned, the philosophy in coding in smart contracts differs a lot, and that's the first difference in coding in Solidity and in normal coding. So, for example, if you are a normal developer, you develop, for example, a Node application, Node.js application, or Java application, and for example, you found a bug or a vulnerability. The first thing that comes to your mind is to fix the code, deploy to the server, and everything is okay. But in the case of smart contracts, if you found a bug or you found a vulnerability, you can't do anything, because if you deploy the smart contracts are immutable. So once deployed, we cannot patch the smart contract. And here it comes the problem in coding in smart contract and security in smart contract. So we should be very, very, very careful before we deploy our smart contracts. So of course, you should write some robust code to deploy it in the mainnet network, in the Ethereum network. But we can do some tests, or just when we found a bug, we fix it. So that's impossible in the Ethereum or in the Solidity concept. But of course, there is some hack around, or there is some turnaround that you can bypass this restriction. Of course, there is some functional, there is some design pattern, like for example the proxy pattern. Basically, the proxy pattern, imagine it that we have a middle smart contract, and we call the middle smart contracts, but this proxy or this middle smart contract calls our main smart contracts. And of course, if we find a bug in our main smart contract, we can just delete the link between the proxy contract and the main contract, and add our smart contract, our new smart contract. But it's very, very difficult, or it's very, very hard to do it. So there is clearly a need for a proper security in the case of smart contracts. So now let's get look at an overall picture in the Solidity or in the smart contracts context. So of course, there is some users that are talking to our blockchain or our Ethereum network. Of course, they are not talking, or they are not communicating directly, but in the bias of a front end, for example, or a website or a mobile application. And of course, they are making some transaction, and making some transaction, it can just sending or receiving some data, or sending and receiving money. And of course, our smart contracts contain some code and contain a storage or a memory. Okay, so that's for the overall picture of how smart contracts in the Ethereum network behave. So now we are going to talk about weaknesses in Solidity, and I decouple these weaknesses to 3 levels. So for the first level, it's about the Solidity, or the language of coding in smart contracts. The second level is the EVM machine. So remember that as I said, that in Java we have JVM, the Java Virtual Machine, but in Ethereum we have the EVM. So the EVM machine they are the nodes that they will run your code or run your smart contracts and execute the call function of that you make. And of course, There is the last level, and it's the blockchain level, and it's the general behavior or comportment or general protocol of blockchain that can handle some problem or can lead to some problem. So I'm going to talk briefly about these vulnerabilities, and then we will focus on some bugs or some vulnerabilities and how to fix them. So first, for Solidity, we have the first problem, and it's named call to unknown. So to give you a context, when we access to the blockchain, everyone has a wallet, and his wallet have a public and private key. So of course everyone here has an address. In the Ethereum case, everyone has an address. So for example, if I want to send you Ether is the money in the Ethereum network. So if, for example, I want to send you Ether, I should know your address. If I know your address, I can send you money. But for example, imagine that I send money to an address that they didn't exist in the Ethereum network. There is no system that will send you back your money and told you, oh, okay, there is no address in the Ethereum network. So when you send or when you call to an address inexistent in the blockchain or in the Ethereum network, your money is gone until, for example, if we found the private key for this address, which is very, very hard to find it. So this is a very, very hard problem in the Solidity or in the Ethereum concept, and the developer should very and should pay attention to where and from the money is sent. So the second problem is gasless send. So to explain more, there is a concept in the Ethereum network, or in Ethereum in general, that is called gas. So as I said, for example, imagine that I have deployed my smart contracts. Now everyone can interact with my smart contracts and make some call function. Okay, so but for example, imagine that we have or for example, the developer can, for example, code a smart contract and he make an infinite loop. So for example, an infinite loop, for example, while true or for, and make an infinite loop that never ends. So here the nodes in the network or the EVM machine will run your code and will go through this infinite loop, and they will never stop running. So they will just run and consume all of resources. So the community or Vitalik has thought a solution to this problem, and by introducing the concept of gas. So gas, it's like its name. So for a car to go from a place to another place, it should have some gas. So same thing in the Solidity or in the Ethereum concept. So to call a smart contract, you should pay to make some to call a smart contract, and how much you will pay, it depends on how much the function have in complexity. So for example, in the case of an infinite loop, you should pay a lot of money and infinite money. So basically you cannot call this function, or you cannot call this smart contract, and the EVM machine will never run this function call. So the second problem here, it's gasless send. So what do we mean by gasless send? So in some functions in smart contracts, and we are going to see them, you can specify how much gas the user or the client will send to you, and you specify the limits. But imagine if we are giving free, or for example, we are not putting any limit in the gas. So everyone can call our function again and again and again, and maybe it can make us some harm. The third thing is exception disorder, and this exception disorder is very hard to tackle it, and but basically I will explain it to you. When we run a normal code, for example, imagine that we are in the case of PHP, we are in the case of Python, for example. So when we run our code, basically we are running it line by line. So for example, we have our main function, and our main function make a call to two functions. For example, a function to fetch, for example, the data clients. Then when we get the data client, we make some special treatment to this data. So that's the normal coding. But in the Solidity case, when we call two functions, for example, I call, for example, a function named or called send money, and I call a second function called, for example, get my awards. So in the general sense, or in the common sense, I should call the function send money first, then call the function of get awards. But even if I call the function send money before get awards, the miner, or the one who will validate your transaction, he can alter the order between these two functions. So he can validate first the get award function, then execute the second function. So that can behave a lot of problem, a lot of behavior that the developer don't want. So there is also some race condition to this problem. So the developer should very be careful. We have also some problems in typecasting. So in the Solidity language, we don't have negative number. The concept of strings it differs a little bit from other languages. It's hard to manipulate strings in Solidity. There is no concept of, for example, pointers. There is no concept of list or dictionary. There is some other structures like mapping. So you should be very careful when you cast a data type or a structure to another structure. The next vulnerability, or the next weakness, is the reentrancy, and it's the most famous weakness in Solidity. Now we still have this problem of reentrancy. In the next slide, we are going to talk deeper in this weakness. And of course, the last thing in Solidity, it's the most famous weakness, it's keeping secrets. So as I mentioned, everything in the Ethereum, or everything if it's a public blockchain, everything it's public. So you should be very careful in the way that you handle data, or in the way that you keep your secrets. For example, there is some schema of commit reveal to put your client in a secure way. They reveal it. So there is a lot of security patterns to do it. The next level is the EVM, and now we are talking about the node, or the machine that will execute your code, or they will execute your smart contracts. So there is, for example, some bugs in the logic of the EVM. There is some problems when transferring an Ether from an account to another account, and there is some bugs. But the most critical thing here is the stack size limit. So when we are talking about stack, basically when we are calling a function, and for example this function are calling another function, and this function are calling another function, the stack size are become to grow and grow and grow and grow, and the EVM has a limit to the size stack. And if, for example, we exceed 1024 for the stack size, an error is thrown and every transaction is cancelled. So we should be very careful. But this problem is already fixed in a recent EP, and there is no problem in the stack size limit. But we should be very careful when we are calling functions and calling another function. Now we are talking about the blockchain level, and we have three things. So first, the unpredictable state. So as I mentioned, blockchain or Ethereum can behave very weirdly, as we normally see in normal languages. So you should not expect that the order of your execution function call will pass in the same order that you call them. The second thing is generating randomness. So this is a very hard problem to fix in the Solidity language or in Ethereum concept on Ethereum network. It's generating random numbers. So for example, if you want to generate a random number in Python, it's very simple. You should just import, for example, random, and you can random, for example, a number between 1 and 100. But in Solidity, the problem here is that the code is public, so everyone can see the code of your smart contract. Everyone can know how you generate this random number, and everyone, if for example, if you add a seed or if you add a salt to the process of generating randomness, everyone can know the seed. So you can't generate a truly random number or just a pseudo random number in Solidity. So here in that case, we are calling an oracle. So an oracle is an API or an application that can do it's external to the blockchain system, and we can keep our secrets in this oracle and call, for example, this oracle, and the oracle will give us, for example, our random number. And finally, the last thing is time constraints, and as you will see in the next slide, there is a lot of problems concerning times in the blockchain system. So now we are going to talk about most famous vulnerabilities in Ethereum that happened, and what's the problem exactly here. So now we have a very famous smart contract called Parity Wallet. So as you say here, we have a contract called wallet. So in the code, when we mention contract wallet, so basically it's like declaring a class or a structure. So now we are declaring a contract called wallet. In the attribute, we have two addresses. We have the wallet library addresses, and we have the owner of the smart contract, the address of the smart contract. The second thing that we have, it's a function called wallet. So as you see, the function here called wallet has the same name as the name of our smart contract. So here it's a constructor. For this example, it's an old version of Solidity. But now we are just calling our constructor public, and you can initiate your construction. But in the old Solidity, to declare a constructor, you should declare a function with the same name as the smart contract. So now, as we see inside of our constructor, we are calling a function called init wallet. As you see, we are calling it by the bias of delegate call, and for this delegate call, it's very hard to make some delegate call without any risks. So you should be very, very careful when you declare a delegate call to another smart contract or to another library. So here we are calling another function in another contract called wallet library and executing init wallet and giving it the address. So if we look inside this function init wallet, and it's in the right side, the wallet library contract, we look into our function init wallet. So the problem here, and as I mentioned, we are calling the function init wallet. We give it just as a parameter, we give it an address, and we make this address, it's the owner of our smart contract. So the problem here is what? The problem here is just this function called init wallet. We have no logic behind it to make sure that that our smart contract or our smart contract called wallet, it's the one that's called this function init wallet. So imagine the case that, for example, a malicious person or a hacker, he will call this function init wallet in the wallet library contract, and of course he will put his address, and he will be the owner of the smart contract. So of course, when he will be the new owner, he can, for example, change the owner, for example, send money if there is any way to withdraw money. So you can do basically anything that is allowed to the owner. So here you should we see the controversy of paying attention to when we call other function in other smart contracts. So basically we should look to the one who is calling our smart contract. Second thing, we should look if, for example, our function or if you want to make a construction function, we should make it by calling it construction and not just making the same name of our smart contracts. Now we are going to talk about the most famous attack in Ethereum, and this attack, it causes the hard fork of Ethereum. So fork, just to explain, as we know, blockchain, it's a list of blocks. So in the Ethereum case, we have a block and a block and a block, and each block is it depends on the block that is behind it. So this the Ethereum network before the DAO attack, it's a list of blocks. But when the DAO attack comes and the developers or the community of Ethereum want to fix this problem, some persons agrees to fix the problem. Some persons say that they will continue with this concept. So a fork happens. So the list of blocks are divided into two lists of blocks, and everyone is happy. And for now, there is the Ethereum Classic, and there is Ethereum that we know now. So in this DAO attack, and as you see, it's a code of 5 lines, and we have a very serious vulnerability. So basically here, what we are doing, so we are mapping some address to some balance or some integer, and we are calling it balance. So a mapping, basically imagine it like a dictionary in the case of Python, or that we have for an key and a value. So here the key is the address, and the value it's the balance of the address of that person. Then we have a function called withdraw. So this function withdraw, it takes in parameter the amount of money that we want to withdraw. So in this example, we called it X. So first of all, of course, I want to withdraw the money from my balance. So first, the smart contract should verify if you already have this money, I can't withdraw, for example, 10 Ether, and in my balance I have just 5 Ether. So the first thing is that the smart contract verify, and they verify it with a simple if balances a message that sender, it's basically the address of the person that calls the smart contract. So we are looking for the balance of the person that is calling the smart contract and verifying that the balance of the person is bigger than the amount of ether that they want to withdraw. So if everything is okay, we pass to the next instruction, and we send him this money. So to send money in the Solidity language, we can do it in 3 ways, but one of the ways is message that sender that call that value, and we are putting the amount of how we will send to him. So in this example, we will send him the value of X, and when I will send the money to the person, or when the smart contract will send the money to the person who called the function withdraw, the smart contract will take the balance, or the variable or the mapping balance, and of course subtraction the value of X. So for the first site, everything looks okay, but here there is some logical problem, there is some race condition problem. So the problem here basically, it's what? The problem here is that after that we send money or we send ether to the person, then we subtract the balance from the variable balances or from the mapping balances. So here it comes the problem. Why it comes this problem? When that value is called, our smart contracts are calling a callback function, and a callback function is what? Basically a callback function. So for example, our smart contracts contain, for example, 2 functions. The first function is called get client, and the second function is called send money. We can make a third function, it's called a callback function. This callback function has no name, and this function it's executed when no 2 functions are not executed. So basically it's just like switch case. So it's switch case, and the default behavior, it's the callback function. So for example, if in the case of our smart contract, we call, for example, get money, and the smart contract will look for this function called get money. So he will find, for example, get clients and send money, but he will not find get money. So in the default behavior, he will execute the callback function, and this can cause a problem. So basically, in the Tao attack, it exploits a vulnerability called the reentrancy attack. So the reentrancy attack, basically it's what? So the hacker will create a wallet contract. So the hacker can create, of course, a smart contract, and the contract that is vulnerable, it's the contract DAO. So in this contract DAO, we have, for example, 200 ether. So now the process of executing instruction in our DAO smart contract, we are validating the balance, it's larger or greater than X. Then we are calling the value and sending the money to the smart contract of the hacker. Now, under the hood, the hacker has put some logic behind the smart contracts, and he put 2 functions. The first function is do withdraw, and inside this function, he just executing a function in the contract DAO, and he is calling the withdraw function and making a withdraw of 100 ether. The second function, and as you see, there is no name of this function, and this is the function that I taught, and it's called a callback function. So this function, basically he will just call another time the function of do withdraw. So now the logic behind it is what? So the first thing is that we are validating the condition of the if. We are sending the money to the smart contracts and giving it 1 ether, but now we are calling our callback function of the smart contracts attacker. And this callback function will call again the withdraw contracts. But now we are not subtracting the X from the balances. So if we run again inside this withdraw function, the condition if will still be valid, and we are going to make another call and sending another 100 ether to the smart contracts of the hacker. And of course, when we send 100 ether to the smart contracts of the attacker, we are triggering the callback function again, and the callback function will just of course call another time the withdraw function of the smart contract, and it will be just like that, and the attacker will just get 100 ether until the smart contract or the DAO contract, the balance of the smart contract will remain 0 ether. So basically it's a famous vulnerability in Ethereum or in Solidity, and it's called reentrancy attack or reentrancy exploit. So basically, to fix this problem, we should just inverse the fourth line, the third line, the line 4 and the fifth line, and make subtraction before sending money, and this problem will be fixed. So you should always make changement to your variable, and in the last thing, calling another function, or for example sending ether. Okay, so there is another solution. There is another solution to this problem, and basically this solution it's very general. In the case it solves also some race condition, and it's like the concept of mutex. And for example, if you want to call a function, or if a person, for example, wants to call a function, he will just as an example, he will lock it with a key and execute this function. So if another person wants to call the same function, he will find that this function is locked, and he can execute this function until the first person finish the execution call and unlock the function, and everyone can execute another time this function. So we can do a modifier called Lockin, and of course require that if for example it's locked, then you should not execute the function, and when for example I finish executing my call function, then I will unlock it. Okay, so that's the problem of reentrancy attack. So I talked about some timing constraint or some order transaction dependency, and I as I said, or as I mentioned, that coding in normal or modern web application or mobile application, it's not like the Solidity. So what's the difference here? So to illustrate this problem, I do a scenario. So for example, imagine that we have a smart contract that can handle a transaction, and it's like a market. It's a smart contract market, and of course we have a seller and we have a buyer, and in this case the seller it's a hacker person, or it's a person that have malicious person. So first the seller will create offer. So he will call a function create offer in the smart contracts, and he will say, for example, I want to sell 10 tokens for 1 ether. So the buyer will see this offer and he will immediately accept this offer. So he will, he will, for example, call the function accept offer and then execute this function. So this is the normal behavior. So everything here it's okay. But imagine that if the seller creates an offer, the offer says that he wants to sell 10 tokens for 1 ether. Then he updated the offer. So he updates the offer and he wants to sell 1 token for 1 ether. So the 10 token will become with 10 ether. And the buyer accepts the offer. So if, for example, we do this in the right order, so first the seller creates offer, the buyer accepts the offer, and then the seller updates offer, there is no problem because the seller has sell 10 tokens for 1 ether, the buyer accepts the offer, and everything is okay. But suppose if the order of execution of this function, and as I said that the miner can control the order of the execution of these calls, imagine that we have create offer first, then update offer, and then accept offer. So the problem here is that the buyer will buy 10 tokens for 10 ethers, and the buyer, without knowing, he will lose 10 ether, and that's a very hard problem to tackle and a hard problem to solve, and how to manage some time constraint without any problems. Okay, there is another problem, and it's a very famous problem, not in just the Solidity language, but also in C, in PHP. A lot of language programmers have this problem, and it's called the integer overflow or the integer underflow. So basically, what is the concept of integer overflow? So imagine, for example, we have a function that is called buy item, or for example, here in this case we have a function called transfer. So we want to transfer some amount of ether to another address. So first we will get the parameter of address. The second thing is the value of, or the amount of the amount of ether that we want to send. So of course, first we should verify that you have already this balance, and we do it with an if or the require function. So if everything is okay, we pass to the next next instruction, and then we are subtracting the balance of the person who is calling this function, and we are adding the balance of the other person that is sending to mine. So everything here seems to be okay, but there is a minor problem. Imagine, for example, if we have 3 ether, and or for example we have 0 ether or 1 ether, for example, and I want to send 2 ether or 3 ether. So the problem here is that when we are going to subtract the balance of our balance, so we are going to take 1 ether minus 3 ether. The problem here is what? So the problem here, as I mentioned, in Solidity we don't have the concept of negative numbers. So when we do 1 minus 3, he will, it's like the counter for a vehicle. So it's like a round, or it's like a circle, and when you are at 0 and you go back, we are going to have 99999. So the same problem here occurred in smart contracts, and for example, if we are subtracting a number and another number greater than the first number, we will find a big and large number, and of course it will cause a lot of problems to your smart contract. There is also another problem called denial of service, and it's a very, very famous problem. And in this case, we have the king of ether problem. So here in this smart contract, it's a very popular smart contract. And basically the idea of this smart contract is that every person can call this smart contract, and of course he can put his money. For example, I put 5 ether, my friend put 10 ether, and the one who has greater or the greater money than the other, he become a king, and he can get all the money. So the basic idea or the main idea of the king of ether smart contracts, it's clear. So but there is a problem here in the logic behind king of ether, and the developer make some bugs or some vulnerabilities, and that can cause denial of service. So basically here in the case of the king of ether, and as we see, we have the first function called refund all, and this function, when someone, for example, become an ether, all the person, we will refund them money. And if something very bad happen, the smart contracts will block and will not be functioning as the normal behavior. So in this example, to exploit the king of ether case, the attacker put a larger number and become a king. But when another person want to become a king, and of course the first process is that we will send back money to the old king, but the actual king can decline this amount, and the transaction will fail. And the smart contract, when the transaction is failed, will not know what to do, so he will be blocked, and no one can call this function, and no one can become the new king of the smart contract. So that's a problem illustrated in denial of service, illustrated in the king of ether smart contracts. So now, as we mentioned some vulnerabilities in the smart contracts, now me as a developer, me as an auditor, or me as a pen tester, what should I do? So first of all, I should not write fancy code. So what do I mean by fancy code? So of course, when the code becomes very, very complex, it's very, very hard to maintain it, and it's very, very hard to secure it. So your code should be not fancy, not complex, not very big. So your code should be very simple to read and clean. The second thing is to use audited and tested code. So that's I see this problem a lot. So for example, in the case of some cryptography mechanism, or some authentication mechanism, or some filtration, sanitization mechanism, some persons want to create their cryptography mechanism, and of course troubles everywhere if you want to do this from the beginning. So every time when you want to do some fundamental things like cryptography, authentication, you should put or you should get the code, the audited code from other entities that they do some researches, or for example some hashes for hash mechanism. It's like, for example, in the case of Ethereum, KiCac 256, but you should not create your proper mechanism because you will get into trouble. So the third thing is keep contracts simple. More complexity, more vector attack, more risks, more exploits. So you should be very, very careful into creating a smart contract. Then you should be always be updated with the software, with the community. Every month a new vulnerability in the smart contracts shows up, so you should be very updated with the community. Then we are going to talk about unit testing. So unit testing, it's very important in the smart contract context. Why is that? So first of all, unit testing, first it ensures that your code is functioning the way that you want. Then, for example, if it's an normal behavior, you will know it through the unit test. So basically, unit test will make some scenarios, and the truffle or the Mocha framework, or there is a lot of framework to do that, will verify that these unit tests are verified. Of course, there is some robust method to do testing, and we are talking here about formal verification, and there is some framework that can do formal verification in smart contract, but it's very hard and very expensive to do formal verification. Basically, for the persons who don't know what is formal verification, it's you use mathematics to prove that your code is behaving the way that you want to behave. We see this in the context of aerospatial or for example aviation systems, SCADA systems, nuclear systems, so to ensure that the system behaves correctly. The next thing is to prepare for failure at any moment. So you should expect at any time your function or any person can call your function, or can call your contract, or you can call, for example, get variables from your smart contract. So you should be very careful in the way that you are calling, or the way that you code your function, and expect the worst thing. And of course, there is a famous thing that I call bug bounty before ICO. So before you deploy your smart contract, and of course after that you audit it with an internal team, you should make some bug bounty to let other person look into your smart contract, and if there is a bug, you will fix it before deploy it to the Ethereum network. And as we said, the smart contract, it's immutable, so once it's deployed, we can do anything. Of course, as a developer, you should also be aware of the blockchain concept, and the protocol that behave of blockchain, the weaknesses, the general weaknesses that we talked about. And we should also make some difference about what is a public function or a private function in Solidity. So for example, in the case of the difference between public and private in the smart contract context, when we, for example, make a variable private, it's not like the normal coding that we cannot access to this variable. Instead, of course, you cannot access it directly, but it's stored in the ledger, or it's stored in the memory of the EVM machine, so we can access it even if it's private. And of course, there is some ways to send Ether or to send money in the Ethereum network. And as I said, there is 3 ways, and there is a send function, there is a call function, and there is a transfer function. But mostly, or in the generous way, we should use send and transfer instead of call, because in the call function we are talking about gasless, or we are mentioning how much gas we will spend on some transaction, and it can cause some problems. So of course, the send and transfer, it's limited to 2100 100 for gas. So you should be very, very careful in executing a call function. And the last thing is avoid external calls, of course, to untrusted contracts or to untrusted accounts when it's possible. So that's the problem that happened in the Parity Wallet, and of course the problem comes to call some or do some external calls to other smart contracts that we don't know how these smart contracts behave, and of course if they have problems and I call a vulnerable function in the smart contract, I can be also affected. So for the last thing is for a pen tester, for example, how I can do some audit, or how can I do some analysis in smart contracts. So the first thing that you need, it's the SOLC, or the Solidity compiler. So the Solidity compiler is very, very important in your work. So you can install it in Linux, in Windows, and you can compile the smart contract live, and then work from the SOC compiler. You can, for example, debug the transaction and make some breakpoints and look into the binary address, look into the memory, how it behaves. So you can do everything here with the Solidity compiler. There is also a tool called Oyente. So Oyente basically it's like GGB or Ghidra for smart contracts. So you can interact with smart contracts, debug transaction, look into the transaction, manipulate transaction, everything you can do with Oyente, and he will look also for some popular vulnerabilities. We have also Remix IDE. So Remix, it's a popular IDE. It's an online IDE. We can code and we can do also some static analysis to this smart contract. We have also Porosity and Manticore. So Porosity, it's a decompiler for smart contracts, and Manticore, it's a dynamic binary analysis. So Remix, it's a static analysis, but Manticore behave in a dynamic way, and it's a dynamic binary analysis, and it supports the EVM machine. Ethersplay, for people who enjoy, for example, Binary Ninja, Ethersplay, it's a plugin for Binary Ninja for smart contracts or for the EVM. Open Zipline, for the Open Zipline, it's a library for writing smart or for writing secure smart contracts. And as we say, for example, the vulnerability of integer overflow. If we use a library called SafeMark, we can tackle this integer overflow and fix the bug. So the two last thing is Solograph and TruffleSuite. Solograph, it's a visualization tool for Solidity, control and call graph. So for example, imagine that our smart contract contains, for example, 100 function. So okay, 100 is a lot of function to analyze. So you should just focus on the main function. So it's a very, very hard thing to do it manually. So Solograph, you just insert him the smart contract, and he will make a visualization with the control flow and the flow and the call flow of functions in our smart contract. So basically, you will look as the smart the function, for example, get clients will call the function get data, and get data will call this function, and you will have a general idea about the smart contracts and how to deal with it, and what is the function that you should focus on finding vulnerabilities and where to look for. And the last thing is the TruffleSuite. So the TruffleSuite, it's a tool or framework used in developing smart contracts. and also it's used for automated contract testing using some frameworks, and every developer should use or do some contract testing. Why is that? Because as we mentioned, that smart contracts, it's immutable, and you should expect everything works the way that you want, and not some, for example, ordering execution, or for example some reentrancy attack, or for example some overflow integer. So you should do some testing to make sure that everything works as fine. So I go to the end of my talk. I hope that this talk was very you enjoyed the talk, and I give you an introduction, or give you an idea about the smart contract attacks. So if you have any question, feel free to ask. So if you have any question about coding in Ethereum, or coding in Solidity language, or security in general in smart contracts, feel free to ask me.